Greetings, my name is 𝗧𝗜𝗠𝗘. I am the Process Optimization Specialist for Lakeside Process Controls and Emerson Impact Partner. So episode 9 of the NTech Toolkit tutorial, we're going to talk about the power spectrum. So in this episode, we're going to cover fast Fourier versus full Fourier. We're going to cover different methods of plotting the power spectrum, as well as how to adjust the scales. And we're going to talk about the cumulative power spectrum and the power spectrum peak. So here I'm just going to read in a file. So I'll read the first file here. And you can see here on the left-hand side, I have the time series, I got the statistics, and on the right-hand side, I got the fast Fourier transform and the power spectrum peaks right here. So just as a gut check, what I'm going to do is I'm going to zoom in and just to see what shape the oscillations are. And you can see right there, the oscillations look more like a shark fin pattern. That's usually associated with a valve that's sticking. If I were to look at the output command of this controller, if it was triangular pattern, it'd be a definite sign that the valve is sticking. All right, we'll just zoom out of that and cancel that. You can see on the right-hand side, it's a FFT, it's a fast Fourier transform. And it goes from the minimum, the fastest frequency it can actually reproduce is 2 seconds. The reason being is that this data sample rate was 1 second per sample. And Shannon's law says that you can only reproduce a cycle that is twice as slow as the sample rate, hence 2 seconds. So here, if I were to actually change the actual dictated sample rate from 1 second to 2 seconds, you could see now the fastest would be 4 seconds per cycle. But I'll undo that right now. And the very slowest that it's representing here is 4,096 seconds per cycle. This is not a coincidence. The fast Fourier actually takes in samples 2 to the x, so this is 2 to the power 12. But you can see here, I got 5,800 samples. That means there's a whole bunch of samples that were not included in that. So the advantage of the FFT, the fast Fourier transform, is that it's a very quick calculation, but it does require a power of 2 number of samples. So what we're going to do now, I'm going to change this. So you go to right click, and I'm going to use a full Fourier. Now the key with the full Fourier is that I will use all 5,800 data points, but it's going to be computationally a little bit longer. It won't be that much here because there's not that many samples, but when you start getting 28,000 samples, 100,000 samples, it may take a few seconds to calculate. So that's the only thing. Next thing I'm going to do is choose a window. So I'm going to choose the Hanning, but these are all the different windows. You can research them all. The Hanning window, every time you do a power spectrum, because it actually assumes that it's an infinite series, but we're only calculating right here and it ends right there. I won't say that I'm actually 100% completely familiar with this, but what it does is that it adds what's called spectral leakage because of the sharp beginning and the sharp end. And that introduces some high frequency components that are probably not associated with that time series. So the Hanning window is there to kind of attenuate some of those high frequencies. So I typically use Hanning. You can experiment with some of the other ones here. So here, before I hit apply, you can actually make this change for this view. I'll probably use this view here, all views and so forth. So here, click OK. So now you can see the difference here. So now it says power spectrum full. You can also see that I've used all the data points to calculate the full Fourier transform right now. A couple of things out here, I can actually do a right click again. And if I want to zoom in, so here, X scale, I can change the X scale here, and I'm going to go 250 origin and a span. So let me make sure it's a span of 250. And now you can see now we got better resolution on that power spectrum peak. And I can also change the Y scale, do a right mouse click, and I can change that to, let's say, 750 and 0. So I can change that like that, and there we go. One couple more things here. I'm going to go to properties here, and no, not properties. I don't want to go to. I want to go to the back to the X scale. Put it back to automatic. Now there are different ways of plotting the power spectrum. The way we're plotting it here is not conventional, because we're plotting it linear period, but actually a power spectrum is calculated on a frequency basis, the inverse of periods. But the reason why we choose periods here is because, as in seconds per cycle as opposed to cycles per second, is because in the process control world, we're dealing with 30 seconds per cycle. You can see down here 95 seconds. If I were to tell you that your level is oscillating 1.67 microhertz or millihertz, sorry, that would be 10 minutes per cycle. It's a little bit easier to understand if I say 10 minutes per cycle as opposed to 1.67 millihertz. So here you can actually change the scaling if you do want to. You go back to properties, and there's your plot setup. So I can set up linear y-axis, but linear frequency. Let's take a look at that. Now you can see everything shifted from the right to the left. Now everything now is equal harmonics all the way across, equally spaced frequencies. And this is what a probably reliability person would be looking at when they look at vibration analysis. I don't normally look at this way, but anyway, the option is there. Another way of looking at it also is log. Now, for those of you who remember, log plots kind of show exponential asymptotes. What I can do is actually read in another file here to demonstrate this a little bit more clearly. And this is the odd time I'll take a look at this as well. So what I'm reading here is a completely white noise signal, random signal, but I filtered it with a low pass filter. So back on the right hand side, you can see here I got my fast Fourier. I'm going to change this, and I'm going to make it again a full Fourier. I'm going to put my trusty handing log, and then say okay. So now, what is a log plot? You can see here a low pass filter attenuates frequencies higher than its cutoff period. And so what it does here, you can see it's relatively flat here until we reach this point here where you can see it starts to drop off, typically minus 20 decibels per decade. So that tells me here, by looking at this, I can actually estimate what the cutoff period is of that filter and calculate the actual time constant. So there's the odd time I will do that. So we'll just close that for now. So put this back to normal, linear period. There we go. And then I'm going to rescale that again, zoom in so we could take a look in more detail those cycles. There we go. So now what you can also do is cursor. So what cursoring does is it gives you the actual value, so the X value. So if I move it across, you could see here this value change and the actual amplitude peak of that harmonic at that particular period. So I can go all the way across here and take a look at that one. So here you can see at X value 100 seconds per cycle, the power spectrum 750. And so you can actually cursor and actually get the actual value. You can see here the power spectrum peaks. And what it does here is actually saying, yeah, you got a cycle around 101.58 seconds. The shape is actually what it does is that it includes multiple harmonics and includes it in the one peak. So it kind of takes an average of all harmonics and gives you 101.58. So here it's actually including eight harmonics in that one particular peak. Incidentally, if you ever see a negative shape, what that means is that inside that, it actually is including the lowest frequency, quote unquote, almost DC frequency at the very, very left. That's what all that means. So I can cursor a little bit more here. There's another peak there at 96.6, which is picking up this one here. It has 3 harmonics. And another one here at 90. So 89, so right here. And I can also move it across right here as well. Right there. And you see 31 seconds per cycle and 30 seconds per cycle right here. So what does these other numbers mean here? Total variance. So this is actually tells you how much that particular cycle is contributing to the overall variance. So what does the variance mean? It means it's the actual sigma of the signal. So the sigma squared is the variance. It tells you the amount of energy it's in the cycle. It is a squared value. And so Parseval's theorem says that the energy in the time series is equal to the energy in the power spectrum, the frequency domain. So if I were to add up all those peaks from the very slowest to the very fast, that would equal to the variance of the signal. So this is another good way to let you know how important is that signal, how much is it contributing to the overall variability of the signal. It tells you the peak to peak, and then if you were to remove that cycle, how much of the variability would remain. So that's very, very useful. So probably bring this back to here. Yeah, I think we're good there. What else is there? Oh, yes, the blue line. So I just talked about Parseval's theorem. So the blue line is called the cumulative power spectrum. It graphically shows how much each harmonic is actually contributing to the overall variance, the overall variability. So what you look for sometimes is sharp increases in this curve, meaning that that particular cycle is contributing quite a bit from here to here in terms of overall variability. You see another sharp increase there, another one there, and another one there. So that's what you're looking for when you want to say, is this cycle contributing significantly to the overall variability? One last thing I want to show you is another way of visualizing it. And this is probably truer than what we're seeing here. Here we're actually connecting the dots, but the actual calculation is actually shown like this, where it will actually calculate at each harmonic, it will calculate the power spectrum value, the power amplitude at each harmonic. And this is the actual true representation. The one I was showing you previously basically is just connecting the dots. So I hope you enjoyed that. Next episodes, we're going to cover the data manager, where it's very easy when you start collecting data. You can get thousands and tens of thousands of files. How do you sort them? How do you organize them when you want to go back and look at them? You can filter through them. You can sort through them by time, by the run number, by tag. You can search the tags. So the data manager is a very, very important feature. Other things we'll look at, importing and exporting data from Analyze is actually very, very simple. And you can import data, let's say, from a Pi historian. It doesn't have to be synchronous data, meaning it doesn't have to be exactly sampled at exactly the same period. It could be asynchronous data. And we're also going to talk about exporting data to Excel, where there, if you want to look at a calculation between two variables, you can export it to Excel, do your calculation, and then re-import them back into Analyze as well. So I hope you enjoyed that, and we'll see you next episode.